morning, everyone. Okay, so welcome to our tutorial 3. Okay, so yeah, I will talk a bit about the project and what's going to happen over the next few studios a bit later. Okay, so for now, let's get started with the tutorial. Okay, so of course, this tutorial is what we covered before the break. All right, and it contains I think at least out of the two which are very important, which is the serialization and the LIDAR. Okay, the ADC for now, most likely you may not use it for the project. Okay, but it's still good to know how it works. Okay, because in future when you are working on some other projects, it may come in handy. Okay. Okay, so let's get started first. Okay, then along the way we will talk about how some of these are related to the project and what we need to know and so on. Right, so in this tutorial 3, we have 3 parts to it. Okay, the first is the serialization. Okay, the second it will be the ADC, and then the third will be on the LIDAR, which we just did. All right. Okay, so for the serialization, okay, basically what we did, okay, if you remember our studio, it had a few parts to it. Okay, so first we did is we had the Arduino Uno, all right, and we actually saw that one way of communicating through serially is through the serial monitor. Okay, so this is the Uno, and this is the serial monitor. Okay, so when you operate through the serial monitor, okay, you can send commands to the Uno, you can retrieve and so on, and that sort of gives you a nice way to interact with your board. Okay, so of course, I think the one thing that you would have, which I also explained in class, is when you talk about any device that displays characters. Okay, so by default, all characters follow this code called the ASCII code. Okay, which you can just Google and get the mapping. All right, that means every character we type actually has a predefined code. Okay, so that is why any keyboard you use for any computing system will always work the same way. Okay, all the codes are fixed. All right, so when I deal with a device or output device or input device that is expecting or generating ASCII codes, I need to be mindful of that. All right, so that is why, okay, whenever I, for example, in my Uno code, okay, if I have a variable x and the answer is 1, okay, I cannot send 1 directly over to the serial monitor. It won't print out as 1, okay, because the 1 translates to another character. Okay, so for numbers, basically, if you look at the table, it starts off with 0x30, okay, all the way to 0x39. Okay, so these are all the numbers that map from 0 all the way to 9. Okay, so that is why if I want to print 1, okay, 0x30 with 0x31 is 1. Okay, so if I want to print a 1 on my serial monitor, okay, I need to make sure I do a add or whatever you want to do. So you can say x equals to 0x30 or with x. Okay, and then I will get the equivalent ASCII value. Okay, so x will now become 0x31. So when I send over, it will print out as character 1. Okay, so similarly, when I use the serial monitor to transmit data to the Uno, I'm also transmitting as ASCII characters. Okay, so if your Uno is expecting is written, or the code is written to look for actual decimal numbers, let's say 1, 2, or 3, then what I need to do is like what you saw in the studio code. I need to take the data, okay, which is the UDR0. I need to subtract the 30. So when I subtract the 30, what is left is that the last digit, okay, which will represent the actual numerical value, okay, not the ASCII value. Okay, so these are some of the things that we need to be mindful of when we talk to different devices. Okay, so within the Uno, everything is fine. But the moment I'm trying to send and receive data across a channel to other boards or other terminals and so on, we need to be careful of how we are transmitting data. Okay, and actually we are going to sort of explore this a lot more in detail in the next few studios. Okay, when we talk about how the whole system is going to come together. Okay, so I'll explain that a bit later. But this gives you the idea that you should always be careful about how data is interpreted by different devices. Okay, the moment the data leaves your current board. Okay, so one of the things that we talked about, or we know, is there's always sort of error or sort of data corruption that can happen. Okay, so when I have a channel, okay, within the board, generally everything is fine because everything is tightly linked together. But when I have two devices connected across some physical channel and transmit data over, okay, there's always a chance that some noise spike will come in, all right, and then you will get affected. Okay, so of course, in the physical sense, there is already some mechanisms in place. All right, so if you look at many cables, they have things what we call shielding. Okay, so some cables that is very sensitive with the data, they have some specific material type of shielding across the wires to protect from EM waves from affecting the data. Okay, then you also have sort of coupling with the ground and things like that. So at the physical level, there are things that they can be designed, okay, so that the cable itself can help to reduce any chances of data corruption. But at the software side also, we need to manage it, all right, and see what we can do. All right, so one of the common sort of techniques that is available in almost all controllers is what we call the addition of a parity bit. So this parity bit is basically an extra bit that is added, okay, so that the total number of ones is either odd or even. Okay, so again, this is again preset. Preset, that means you already decide beforehand that the transmitter and receiver must agree. Right? It's just like when I preset that I say that I want to transmit as 9600 bps, then the receiver must also be 9600 bps. All right. So similarly, the odd or even parity configuration must also be agreed earlier on, and both transmitter and receiver must already have the same setting. So a simple example is this. So if I say odd parity, means the total number of ones is odd. Okay, so if I look at the actual data here, I have 1, 2, and 3 ones. Okay, so 3 is already odd, so the parity, I don't need to add anything. Okay, whereas if I had even parity with the same data, so 1, 2, and 3, so I have 3 ones, so I need to add one more, so it becomes 4 ones, which is an even number. Okay, so the parity bit will be automatically generated, so you don't need to do it. Okay, it'll be automatically generated by the hardware. Okay, so the hardware itself will generate based on the bits that we set to ensure that the correct parity bit is generated and added to the data. Okay, so even though we have this, okay, it is still not reliable. Okay, so not reliable. Okay, why is it not reliable? Okay, because parity checking can only detect odd number of parity errors. Okay, so what do we mean by that? So if I take this data packet here, okay, if I take this data packet here and I say I'm using even parity, okay, that means I expect even number of ones. Okay, so when I transmit the data, since I have 3 ones over here and I expect even parity, so I add an additional 1. Okay, so I have a total of 4 ones in the whole data packet. Now I transmit this across the channel, and at the receiver side, I receive again a data packet. But what do you observe in this received data packet? You observe that 2 bits have actually flipped. Okay, 2 bits have flipped. All right, so this 0 has become a 1 and a 1 has become a 0. Okay, and if I want to do the parity check, okay, you will see that I still have 1, 2, 3, and 4. So I still have 4 number of ones, which is agreeing with the even parity. All right, so we are still not able to detect that an error has occurred. All right, so this is of course not a very foolproof system. So that is why we are going to be exploring other types of mechanisms such as checksums and CRCs. Okay, we will be doing this in the next few studios. Okay, so what causes corruption? Okay, so any interference from any other external noise. Okay, so basically when data is transmitting, okay, even though we draw it ones and zeros this way, it is never so perfect. All right, it's never so perfect. There's always some noise. Okay, so there's always some noise present. Okay, and in some cases the noise can be even more when the channel is longer. Okay, that means if I have a longer channel to transmit the data, okay, you won't even get something so smooth. You probably get something like this. Okay, then along the way, of course, as we know, our environment is filled with EM waves or electromagnetic waves from any device that is nearby. Okay, so there's always a chance that at that point of time, maybe there was some equipment that just switched on beside that particular board and it caused a spike in the EM wave. All right, and that can suddenly cause a spike somewhere in the signal. So what is supposed to be a 0 might be interpreted as a 1. Okay, so these are things that can happen in real world. Okay, because you can never control the environment. All right, so that is why there is a certification, all right, to minimize the interference caused by one equipment to another. Okay, if you look behind all your electronic devices, somewhere there will be some sticker. Okay, there will be some sticker that looks something like the CE or something. Okay, so and there'll be a few other stickers. So all these stickers and so on sort of tell us that they have gone through the certification to verify that the amount of EM waves and interference that it generates is acceptable. Okay, because you do not want to buy a product that once you put it in your house, then everything else doesn't work properly. Okay, so there is a certification body that looks into measuring the amount of interference that one device can cause to another device and so on. Okay, so things like that. All right, so in real world, a lot of noise is present in the environment. Okay, so we need to make sure we are able to handle it correctly. Okay, and so in the next, I think next week's studio, when we are going more deeper into the communication protocol, we're actually going to be looking at checksums on how we can generate that to better detect errors in the system. Okay, so this one I think is quite straightforward. Sketch the frame and so on. So I think you can just take, for example, one example here. All right, so if you notice the start is always a high. Okay, because the idle line is always high. Okay, so by default, when you look at your serial line, if you hook it up to oscilloscope, you will realize that by default is always high. So the device that wants to start transmitting data will always pull it low. So that is always the start bit. The start bit is always a high to low transition. So that when a high to low transition is detected by the receiver knows that, okay, data is coming in. Okay, and subsequently you have all the data over here. Okay, so of course, once it detects the high to low transition, you will need to start sampling. Okay, you need to start sampling, and how fast it sample, again, it depends on the pre-configured port rate. Okay, so you will know that, okay, if I configure at 9,600 bits per second, at what frequency should I start to sample, or what interval should I start to sample my data? Okay, so again, your data will come in. Okay, maybe you have 2, 1, something like that. Okay, then eventually after everything is done, okay, then maybe you have one more parity bit. Okay, and then finally you have a stop bit. Okay, so the stop bit is always a high bit. Okay, so 0, 1, 0, 1. Okay, maybe I will. Okay, so maybe I just draw one particular example here. Okay, so you can see that this is the start bit here. Sorry, this is the idle line. So start is 0. So 0, 1, 0, 1. So 0. So the first after start will be 0. All right, then will be 1. Okay, then 1. So 0 again. So this is the 0, 1, 0, 1. Okay, 0101 0110 0110. Then 0. Okay, and then finally you pull up. That's your stop. Okay, so again, you can just hook up your scope, okay, to your transmit line of your Arduino, okay, while you're sending some data out, and you should be able to see something like this. All right. Okay, so let's go on to the next question. So in this question, they're asking about parity across bytes. Okay, so we know that in the earlier example, when we looked at a single bit parity generation, there are already issues because you can only detect you can only detect odd number of errors. Correct? If it's even number, you won't be able to detect. Okay, and at the same time, you also do not know where the error is. Correct? You know there's an error, but you do not know where the error is. Okay, so one way of trying to figure out where the error is by computing the parity across bytes. Okay, so if you look here in this system, we compute across every 3 bytes. So for every byte that you have, okay, you can see that I generate 1 parity bit. Okay, so in this case, we are having an odd parity system. So if I just take the first byte, I have 1, 2, 3, and I have 4 ones. Okay, so in an odd parity system, if I have only 4 ones, then I know that there is some error in this particular byte received. Correct? I know there's an error in this particular byte 1 that is received. But I only know there is an error, but I do not know where the error is. Okay, I do not know where the error is. So if I don't know where the error, then that is where the second level of check comes in, which is the computing of the parity across the bytes. So now for each of the bits, I compute the parity across them. Okay, so when I compute, you will see that here I have only 1. So here is 3. So all is odd. But here is the only one where I have 2. So it's also even. Okay, so it tells me that there is an error in this particular column, in this bit 4. So in bit 4, there's a column, and in byte 1, there is so in bit 4, there's an error, and byte 1, there's an error. Okay, so with these 2 bits of information, you can narrow down and say that this is the bit that has flipped. Okay. All right, so this is again one of the other techniques that you can use to detect errors. Okay, again, there are many different approaches out there. Okay, but we will cover more in the next video. Okay, one of the techniques is the checksum and CRC. Okay, but of course, you can always explore other techniques that you read up on when you are working on something on yourself. Okay, in this question, we are looking at transmission time. Okay, so in this, we are saying that how long does it take to transmit all 128 bytes in a buffer, okay, at 9,600 bps with 8N1 framing. Okay, and what implications does it have on how fast a program can write to the buffers? Okay, so in this example, basically what is happening is you have a buffer, all right, and you can store total 128 bytes. Okay, and you want to transmit this out, okay, on the channel. Okay, of course, this is a buffer. So a buffer is just like a storage space, right? That means you have some other application, okay, your application that will want to update this buffer on a regular basis. Okay, and whenever I update the buffer, I will send out. All right, so how frequently can I, okay, what's the periodic interval at which I can update my buffer? All right, so in order to know how frequently I can update my buffer, I need to know how long it takes, okay, for my buffer to actually finish transmitting the data out. All right, so of course, that is where all this calculation comes in. So the first thing that we look at is the number of bits I need to transmit out. Okay, so in 8N1 means I have 8 bits of data, which is this. Plus I have one stop bit, all right, and one start bit by default. So N means there is no parity, so there is no additional bit. All right, so technically one data packet is actually a 10-bit frame. Now one data packet is actually a 10-bit frame. All right, so now I am transmitting out at 9,600 bits per second. Okay, so if I divide that by 10, it is 960 bytes, okay, per second. So of course, in this sense, maybe instead of calling it byte, we can call it a data packet, because byte may be associated with 8 bits, correct? So in this case, instead of bytes, you can just sort of think of it as a data packet. Okay, so you are able to transmit out 960 data packets per second, and each data packet is actually a 10-bit frame. Okay, and I am supposed to transmit 128 bytes. 128 divided by 960, I get 0.13 seconds. Okay, so it takes me 0.13 seconds to transmit data, okay, from my buffer out, okay, through the UART line. So this is 0.13 seconds. Okay, which means that I can only update with a new data into the buffer after I finish 0.13 seconds. Okay, of course, in a actual implementation, you would not generally do a timing based approach. Okay, generally, if I were to do this as a project, I would not write a code to wait 0.13 second and then write 0.13 second and write and so on. Okay, what I would normally do is I would want to make the system generate an interrupt. Okay, to generate some interrupt in a way such that I know that when I finish, I get a notification. Okay, so that the moment the notification comes in, I will be able to proceed on to load the next set of data to the buffer. Okay, that will be a more efficient way and more sort of accurate way of doing it. Okay, because this 0.13 second is not, I mean, for theoretical sense, we can say we calculate and say this is the number, but in a practical sense, nothing is perfect. All right, so you can't say for sure that this entire 128 bytes will keep going out without any delay, without any error or something. Okay, so in some cases, maybe you took slightly, the UART took a bit longer to update one of the register. Okay, and so on. So it is not to say that this will go on perfectly at the same rate all the time. Okay, but this will be the general rate. All right, so instead of using some timing approach in a solution, it's better to use some notification approach. That means once I finish, I'm notified, okay, maybe by interrupt or by some flag, global variable flag or something, and then I do the next. Okay, so the frame, okay, if I add one more stop, if I add instead of 8 data bits, I have only 7 data bits, then this will become 9 bits. Correct. If this becomes 9 bits, then the effective rate will become slightly higher. Correct. The effective rate becomes slightly higher. That means I can transmit the 128 data packets slightly faster than 0.13 seconds. So the frame is basically how much data I have to transmit. Okay, every time I look at 1 byte of data. Okay, so that again, like I said, all this calculation is again theoretically we can say that this is the answer. Okay, but in a practical solution, we need to think of what is the more optimal way of implementing it. All right, that can be more efficient. Okay, so let's just have a quick recap of the studio. Okay, so the last activity in the studio, okay, I'm not sure how many of you managed to reach that part. Okay, but we will be coming back to this again and again. Okay, over the next few studios. Okay, because basically forms the backbone of the entire project that you're going to work on. Okay, that the Rpi and the UNO must talk together. Okay, so for the Rpi and UNO to talk together, there are actually a lot of challenges. Okay, not so straightforward. Okay, and we will be covering all of that in the next few studios. Okay, but for now, what have we done? Okay, so the first thing is the Rpi itself is running on 3.3 volt. Okay, and the UNO is running on 5 volt. Okay, so rightfully, when you have devices on different voltages talking together, okay, you may need something called a voltage translator. Okay, but in our case, we don't need it. Okay, because of the way Rpi handles the data when 5 volt comes in, and 3.3 is also interpreted as a logic high in the UNO. Okay, so because of that, this voltage translator is actually not needed. Okay, but I'm not so sure whether we are still going to use it. All right, but this part we'll come back to it again next studio. Okay, of course, having a voltage translator is good because it can ensure that the correct voltages are translated. Okay, so if I transmit a 1 and a 0 here, okay, so even though this is 3.3 and 0, the voltage translator will make sure it is 5 and 0. Okay, then the other way around is the same thing. Okay, so this part we will look again, okay, the next few studios whether we still have this in our project kit or not. Okay, so the next thing that I want to talk about is how the data is processed. All right, so the Arduino uses interrupts. All right, so we already saw this in the studio that we configure the UART transmit interrupt and receive interrupt. Okay, so that whenever we want to transmit, use or receive, we use either of the interrupts. Okay, now how about the Rpi? Okay, does the Rpi also use interrupts to do transmit and receive? Okay, so this is coming back to the last section of your week 6 studio. All right, where they ask you to look at the code. Okay, so if you were to look at the code, okay, that is given, okay, an Rpi code, okay, what you will see is something like this. Okay, so I'm not sure again how many of you reached this stage, okay, but the key thing that I want to highlight here is if you look at it, okay, this is the part where we do a serial write. So this is the transmit, and this is where we do a serial read. So this is where we do a receive. Okay, and both of them are inside the same sort of main loop here. Okay, but yet your Rpi can transmit and receive at the same time. Okay, without any issue. Okay, because of this thing called fork. Okay, we are not going to go into all the details here. Okay, but this ties in with again something you will learn in used to be year 2, now it become year 3. Okay, 2271. All right, where you will be able to develop what you call multi-threaded code. Okay, that means each of or each sort of task will run on its own. Okay, so what fork does is it actually helps to separate out the transmit and receive to 2 branches. Okay, so you can think of it as 2 parallel branches of code running at the same time. Okay, so one branch will run this transmit code, the other branch will run the receive code. Okay, and that is possible because we are running the Linux on Rpi. All right, so it supports multi-threading. Okay, so for now, just take it that in your Rpi, because we are running a multi-threaded OS, we can actually do fork and allow 2 tasks or 2 threads to run concurrently. Okay, one task to do transmit, one task to do receive. Okay, so that is how the Rpi is actually managing it. Whereas on the Arduino, we are still having a single threaded environment. Okay, we have not done any multi-threading on the Arduino. So that is why the Arduino still manages it using the interrupts. Okay, so it's 2 different frameworks, but they both work very nicely together. Okay, and this, like I said, this sort of is the backbone of the whole system. Okay, and your project is going to be built based on this framework. Okay, so what you did in the most recent studio is your Rpi, you know, it talks to your LIDAR. Okay, so you have your LIDAR here, okay, that is spinning and collecting all the data from the environment. All right, and what we will be doing is this LIDAR data, okay, you will be able to visualize it, okay, using your GNU plot or RBase or whatever. So you have your RBase or your GNU plot, okay, whichever you want to visualize the map. Okay, so while you're moving, you will see some lines, you see some lines, okay, then you see a gap, then you say, okay, I need to go in this direction or something like that. Okay, so that is one part. So on the navigation, okay, or the environment mapping, you already saw the Rpi and the LIDAR, okay, and you saw either RBase or GNU plot, okay, to visualize what the LIDAR is telling us. Then at the same time, okay, if you remember the video that I showed you yesterday, the operator is continuously sending commands. Okay, so that in your screen, in a whole sort of big computer screen, okay, one of it will be this, then the other one will be actually a serial terminal, okay, to send commands, okay, forward, right, left, something like that. Okay, so you keep sending some commands continuously, and these commands are actually sent from the Rpi to the UNO. Okay, so you are going to use a terminal, okay, a simple, okay, just a simple text terminal to send commands, okay, from the Rpi to the UNO, and the UNO is the one that is connected to all your hardware. Okay, so your wheels, okay, your wheels, okay, your motors, everything. All right, and all the motor drivers. Okay, so all those things that you did in the first half. Okay, the DRB driver chip, okay, the PWM control, and your GPIO. So all of that will be integrated inside your UNO code here. Okay, and when we send the commands over, okay, whether it's forward, reverse, left, whatever, your UNO will be sort of decoding that information, okay, and making the robot move in that direction or in whatever that you want it to do. Okay, so the Rpi is very much the brains, okay, or the control center of the whole system. Okay, because that is the one that gives you your plot, and you use that to also send commands to the UNO. So the UNO is very much a slave. Okay, it's just waiting for commands to be received from the Rpi, and then you will act accordingly. All right, and at the same time, of course, we also are able to get back information. So in the past, I think from the video I showed you, that we used to have some obstacles, not obstacles, some objects, colored objects at some part in the maze. Okay, so your robot must go there and do some color detection. Okay, so the students had to fix up some sensors, okay, to do some color detection. And then when you detect some color, you must be able to send the information back to the Rpi, okay, on what color you detected. All right, so that is basically the whole framework. Okay, of course it looks complicated. Okay, it looks complicated, and it is complicated. All right, but again, the next few studios, I would say about 90% of the code is already given to you. Okay, 90% of the code for the Rpi as well as the UNO is already given to you. Okay, to do all of this stuff. Okay, so this 90% covers the entire. I mean, the LIDAR you already have. Okay, and this entire communication framework, which is what will be given to you. Okay, the device drivers and all those are your own code. Okay, how you control the motors, how you want to control any sensor. Okay, all of that is whatever you have developed over the last few weeks. Okay, but the entire communication framework, everything will be given to you. Okay, you just need to, in the studio, we'll ask you to do certain things to just try out and make some improvements to the framework already given to you. Okay, so that is again the whole thing. Okay, and over the next maybe 2 to 3 studios, we will actually be exploring and working on this. Okay, to make sure that everything comes together. Yeah, so Rpi doesn't use interrupts. Rpi uses fork, okay, to manage both of them concurrently. Okay, so yeah, we will come back to this whole picture and framework again and again as we go through the studios. Okay, so let me just do a poll here to see whether everything is okay so far. So you just need to, I think you've done this before, correct? Just open our browser, go to this link and answer whether it's true or false. The link is at the top. This link here, polev.com/rsnus. Okay, so you just open up any browser on your phone or your laptop, whatever. Go to the link, then you will be able to answer it. Okay, so there's a question on whether we can use the UNO libraries. Okay, so I'm not sure whether the grading framework is given already, but basically over the last the general grading framework has always been that if you use the bare metal code, okay, then you get the full marks for the implementation. If you use sketch programming, which is basically using the libraries, then for that particular component, you get only a fraction of the marks. Okay, so that has been the case always. All right, so you need to make sure you use bare metal coding, which is basically what we have been doing over the last few weeks. Okay, when you want to develop the drivers for your motor control or anything else on your Arduino Uno. Okay, so you can still use Sketch, all right, but again, if you use Sketch programming, you won't get the full marks for that portion of it. Okay, so let me end this poll here. All right, so basically, it's asking whether the parity bit can help us detect and correct single bit errors. Okay, so the keyword here is correct. All right, and for what we discussed, we know that a single bit error can be detected, but the system in the AD328P cannot correct it. Okay, we can only know that the error has occurred. Okay, but we do not know where the error is. Okay, so we can detect it, but we cannot correct it. Okay, of course, unless you do a lot of other stuff like maybe you do the parity check across bytes and so on. Okay, but by default, the system within the microcontroller itself cannot detect, cannot correct the error for us. Okay, it can only detect that there is an error. Okay, so let me do one more poll here. So this one is you need to type in something. So what exactly is baud rate? Okay, because when we talk about the UART, okay, and usually when you talk about any form of serial interface, you will see this term very frequently, baud rate. Okay, so what exactly is baud rate? Okay, so sorry, rate at which information is transferred, qubits per second, bit rate. Okay, so generally, I think most of you get the idea, which is good. Okay, so let's discuss this a bit. Okay, so in most cases, I think one of the common thing is we call it bits per second. Okay, but generally, baud rate. Okay, generally baud rate is equivalent. Okay, to what we call symbols per second. Okay, symbols per second. And again, by default, we tend to think symbols in terms of ones and zeros. Okay, so we equate it to bit rate. Okay, but it's not necessarily bit rate. Okay, so why do we not generally equate it to bit rate immediately? Because a symbol can represent more than a single bit. Okay, more than a single bit. Okay, what is an example? Okay, I'm not sure whether you already covered any sort of communication modules. Okay, I mean, in terms of the data transmission. Okay, like modulation techniques and things like that. All right, so if I want to transmit data from one place to another place, of course, I transmit based on the symbols that I have. So if I have ones and zeros, then the data will be ones and zeros only. Okay, so that is what we know. But I can also choose to represent my data in more than just two ways. Okay, so what are more than two ways? Okay, when we say ones and zeros, we are limiting ourselves to two particular voltage levels, correct? 0 and 5 or 0 and 3.3 and so on. Okay, but what if I were to break it up into different levels? Okay, break it up into more distinct levels. Okay, that means I can say that I have, instead of just 0 and 5 or 0 and 3.3, I maybe have 0 volt, then 1.25 volt, 2.5, okay, and then 3.25, something like that. Okay, so let's assume that I have 4 different voltage levels. Okay, that means I can send a symbol like this, I can send a symbol like this, or a symbol at each of these 4 voltages. Okay, so if I choose to send data like this, where I have 4 distinct voltage levels, and if I have 4 distinct voltage levels, so 2 to the power of 2 is 4. That means each symbol is 2 bits. All right, that means when I send this kind of a data over and I sample it, okay, when I sample it, what happens? That means I'm actually decoding 2-bit information, because this could be interpreted as 0, 0, this could be 0, 1, 1, 0, and 1, 1. So I'm still transmitting a symbol. Each time is a symbol that is a distinct voltage level, but that symbol is now representing 2 bits at each time. Okay, so that is the difference. Okay, so when we say baud rate, okay, generally we assume it's bit rate, okay, in most digital logic systems. Okay, but because we can modulate the signal with different techniques, okay, so because of that ability, we need to be mindful that a symbol may not always relate to a single bit. A symbol can represent 2 bits, can represent 4 bits, and so on. Correct. So the same thing, if I break it up into 16 different levels, that means I have 4-bit information. Correct. That means one symbol represents 4 bits of information. Okay, so you can see that I can immediately double up my data rate. Okay, if I use this to transmit my data, I immediately double up my actual bit rate. All right. So again, these are just some of the things that we need to be aware of. Okay, so when we say baud rate, it's actually symbols per second. Okay, not always bits per second, even though that is a general sort of understanding. Okay, so I think we can just go for a short 5 minutes break. Now is 9:50 or 9:47 or so. Let's just go for a 5 minutes break. 9:55. Okay, for 7 minutes time, 9:55. I'll see you back here, and then we will finish up the rest of the questions. Okay, so just have a short 5 minutes break. Okay, we'll come back. So if any questions, you can just put in the chat. Later, I will address those questions. Okay, so welcome back. So let me just answer some questions here. Okay, so for this slide, there is error just now. I think there was this two. Just now it was 101011. Okay. So there's a typo here. So they missed out this additional 0 here. Okay, so here got 2 zeros. Earlier there's only 1 0 in the answer. Okay, so there'll be 2 zeros here. Okay, so just take note of that. Then another question is this. Okay, so basically how we get 0.13 seconds. If since one data packet is 960 based on the 9600 bits per second, and one data packet is 10 bits, okay, which means I can transmit 960 data packets per second. Okay, and since I only want to transmit 128 data packets, so it's 128 divided by 960, it should give me 0.13 seconds. Correct? It's just the ratio of how many data packets that you are transmitting given the current baud rate here. Okay, so let me go ahead first. At the end, if you still have questions, I'll stay back to address those questions. Okay, so in this next part, we are going to be looking at the ADC module. Okay, okay, so the ADC module is, I think, a very useful module. Okay, because even though most sensors right now have a digital version, there are still sensors out there that are still sort of giving you an analog output voltage. All right, so we want to be able to deal with that. Okay, so of course, when we have an analog voltage, okay, before we digitize it, before we do ADC sampling, we need to do something else, which is the signal processing, correct? Okay, so this one, I will not go into that. Those of you who have done EPP1, okay, you already know what we're talking about. That means things like any filtering of the signal, amplifying the signal, the gain using op-amp or things like that. Okay, so you may want to do some first level processing of the signal to match the ADC input range. Okay, again, this is very important when your signal is, let's say, very small. Okay, your signal is very, very small. Okay, maybe 0 to 1 volt, okay, or 0.5 volt, but your ADC is from 0 to 5 volt. Okay, so you want to extend the range of it, okay, using a operational amplifier and providing the necessary gain and things like that. Okay, so that one, again, we are not covering. It's not part of this module. If you have done EPP1, you know what I'm talking about. If you have not done EPP1 with us, all right, then this is something that you may want to look into. Okay, how to use an op-amp, okay, to do some gain, okay, or to provide some gain, and to also do some filtering of the signal, okay, before we do A to D conversion. Okay, now in terms of A to D conversion, we have a 10-bit ADC module, okay, within the AT328P. All right, and we know that most of the registers that we use are 8-bit. Okay, so when we wanted to update the OCR register value, we had to scale it down. All right, so one of the easiest way to scale it down is we discard the lower 2 bits. All right, so if you remember, if I have my total result, which is 10 bits, which is 9 to 0, the results, and I want to bring it down to 8-bit 0 to 7. Okay, one way is I discard bit 0 and bit 1. Okay, so basically the 9 to 2 will map to 7 to 0. Okay, that is the same thing that you do when you divide by 4, right? Because every time you divide by 2 is right shift by 1. So divide by 4 is right shift by 2. Okay, so divide by 4 is equivalent to right shift by 2. Now, that is again something that we can do to scale a 10-bit result down to 8 bits. Okay. Now, what are the other alternatives, okay, that we can use to directly obtain an 8-bit result, okay, without having to do any other work? Okay. So one of the things that this controller provides is this ability to decide how the 10 bits are going to be stored. Okay, so by default, what happens is the 10 bits is broken up into 2 registers, ADCL and ADCH. Okay, and what happens is the default setting is ADCL has the bits from 0 to 7, and the ADCH has the bits 8 and 9. Okay, but this 8 and 9 is actually in bit position 0 and 1 of the ADCH. All right, so this is the default sort of setting when we look at the result. All right, now what we this is called the write justified mode. All right, and in the controller there is actually an option where we can set this AD LAR bit, okay, to decide to switch it to a left justified mode. All right, so that is inside this AD marks register, this bit file over here. So what is left justified and what is right justified? Okay, so in right justified, this is what you have. Okay, so the lower 8 bits are in ADCL and the ADCH only has the 10th and 9th bit, the upper 2 bits. But if I choose the left justified approach, what happens is the data, the upper 8 bits are stored in ADCH and the lower 2 bits are stored in the ADCL. All right, so when I look at it this way, what do you see? You see that if I wanted to scale 10 bits down to 8 bits, I want to discard the last 2 bits. And in this mode of operation, the last 2 bits are already in the ADCL register. And the upper 8 bits, which I want, are already inside the ADCH register. Okay, so this upper 8 bits that I want are already available in the ADCH register without me having to do anything. Okay, the 8-bit result is already there. Okay, so I can straight away use this left justified mode and just read the ADCH value. And by doing that, I actually get a sort of 8-bit scale value. All right, so this is again just to sort of highlight some of the features of the ADC controller that we didn't get to explore in the studio, but now we understand that these are some of the things that are there that could have actually helped us as well, okay, in doing some of the ADC conversion and scaling. All right, so that is the left justified and right justified approach. Okay, so the next question here is to sort of better understand how this particular ADC module works. Okay, in terms of ADC module, okay, there are a lot of different sort of hardware designs that can be implemented to perform an A to D conversion. All right, so if you look up any electronics book or any resource on how to build your own ADC module, okay, they will come up with a lot of different circuits, different ideas about it. So one of the techniques is what you call the successive approximation ADC. Okay, so this successive approximation ADC technique is what we're going to be discussing. All right, to give you a better idea of exactly what is happening. Okay, how does it work? All right, so if you see down here, okay, when we start the ADC unit, okay, the sample and hold unit, okay, so come back here. All right, so what happens is the sample and hold, so this part over here, is the ADC channel that we are converting. Okay, so this sample and hold basically means that I am taking or sampling the value at that particular time, okay, based on the sampling rate. Okay, so that is the first thing I'll do. I'll sample the data and I'll hold it. Okay, when analog signal is at the input. And what I will do is I will generate a binary code. Okay, with all bits clear and the most significant bit set to 1. Okay, that means this hardware here will at the very first time generate a 10-bit result where the most significant bit is 1 and everything else is 0. Okay, and then it will be 2.5 volts. Okay, because that is the turnover point, right? The most significant bit switching from 0 to 1 in any number of bits is always the midpoint. It is always the midpoint. So in this case, it will be 2.5 volts. And then what I will do is I will do a comparison. Okay, so if you look back at the circuit here, this is nothing more than a comparator that compares the output of the positive and negative terminals. Okay, and once I compare, I will be able to decide, okay, whether to keep the bit or not to keep the bit. So if the current signal that I'm sampling is bigger than the digital to analog output, then I keep the bit. Okay, if not, I clear the bit. Okay, and then we keep on repeating it. Okay, so let's just see this step by step. So it's easier to work with real values. So let's assume that the input signal that I want to sample is 3.6 volts. So when the 3.6 volts comes here, okay, when the 3.6 volts comes here, the very first time I will generate this over here, 1000, okay, as the conversion logic output, and that will translate to 2.5 volts here. All right, so when I compare 3.6 and 2.5, we can say that 3.6 is bigger than 2.5. Okay, if that is the case, that means the output of the op-amp comparator is true, then I keep the bit, so the 1 is kept. Okay, then I go on to the next bit. Okay, so I do bit by bit, starting from the most significant bit down to the least significant bit. So now I go to the next bit. So this first bit I already know I'm going to keep it. Then I change the next bit. When I change the next bit, again the next same thing happens. I will generate a new voltage. Okay, so how do I relate the voltage to the bit position? Okay, so it is equivalent to how we deal with numbers. Okay, every time I right shift by 1 is equivalent to divide by 2. But if I left shift by 1, it is equivalent to multiply by 2. Okay, so we relate the voltage levels in the same way. So when my most significant bit is 1, and everything else is 0, then I say that is 2.5 volts. If I were to do a right shift by 1, so the 0 is here and the 1 is here, then it will be half of 2.5. All right, then if I shift by 1 more again, it will be half of 2.5 of half of that. Correct, so this will be 2.5, this is 1.25, and this will be half, and so on. Okay, so that is how you can relate a particular bit position to voltage. Okay, it's the same as any right shift and left shift. So if I go in the other direction, whenever I go to the left by 1 bit, I am actually multiplying by 2. If I go to the right by 1 bit, I'm actually dividing by 2. Okay, so every bit actually corresponds to a particular voltage level. Okay, so with that, we can say that when the second bit is 1, so this is the first bit. Okay, this is the second bit. Okay, so when I say first and second, I'm coming from the most significant bit. Okay, so the most significant bit is 1 is 2.5 volts. When the second bit is 1, it is half of 2.5. So it's 2.5 by 1.25. So the total voltage that I will generate, okay, from the conversion logic, the digital to analog converter, will be 3.75 volts. Okay, so when I get 3.75 volts and I do the comparator check, I will realize that actually 3.6 is bigger than 3.75. So if it's bigger, then I clear the bit. So the first bit was set, second bit is cleared. Then I move on to the next bit. All right, and then I keep repeating this. Okay, every time I toggle a bit, I check what is the new voltage, and then I check whether my current voltage is bigger than the new voltage. If it's bigger, I keep. If it is not, I clear. All right, then I keep doing it until I reach the last bit. Okay, so this keeps on going. Okay, until I finish all the 10 bits. And when I finish all the 10 bits, all right, again, this is the whole sequence. These are all the values you will get, and you'll get the final answer over here. So this is basically what is happening, okay, within the ADC module whenever you start a conversion. Okay, whenever you start a conversion, okay, this is what is happening. Okay, it is going through this process to generate that final 10-bit result for us. All right. Now, of course, in terms of calculation, we don't need to go through this process, correct? We can just directly, okay, take 3.6, which is the voltage, divided by 5, multiplied by 1024, okay, which is what you did in your studio. Okay, and then from there you can get the actual binary value immediately. Okay, so you can immediately calculate it, okay, but in order for the ADC module to generate this answer, it actually has to go through the entire process, okay, for all the 10 bits before it can give you the answer. Okay, so this sort of gives you, this question is to sort of to understand what is actually happening within the ADC module whenever you start a conversion. Okay. Okay, so that sort of wraps up the ADC part. So I just have one question. Again, just share your answers here. So you start a project, okay, with the 328 pin, and later you realize you need a 16-bit ADC module. So what do you do? Ask Prince for help. Okay, take the 10 most significant bits. SU. Okay, so maybe in case you haven't realized, this module you cannot SU. Okay, I'm not sure whether you are aware of it. Okay, this module you cannot SU because it is coded as a 2000 level module. All right, so EPP1 you could SU, okay, but this EPP2 you cannot SU. Okay, so no, like Prince is a very popular guy in the lab. It's good. Okay, so why I ask this question? Okay, why I ask this question is this is, I mean, though it's about the ADC module, but this issue of realizing halfway through that something is not there is quite a common sort of setback that most students face, especially when they're working on some final year project or something on their own. Okay, and this usually happens because when we start off the project, we may have made certain assumptions, or we may have sort of did not foresee some of the requirements or review the requirements very carefully. Okay, so we thought that maybe this particular microcontroller is enough. Okay, and then we start the project, and more than half of the product is done, and then you realize you need something which is not there. You need something which is not there. Okay, so in that sense, okay, you are stuck, right? You are stuck because how do you proceed? Okay, so again, some of you I think gave some good suggestion. Okay, scale down the input signal, shift, take the upper 10 bits, and so on. So I would say these are all very practical and valid options that you should consider. All right. Okay, because to dump your work that you have done over the last few months and then switch to another controller and start all over again, it can be a very stressful thing to do. Okay, especially if you have a deadline to meet. Okay, so you need to probably question yourself whether you really need this 16-bit ADC module. Can you make some software tweaks and adjustments later on by just using the available 10-bit module? Okay, okay, or the other option is, of course, you have an external 16-bit ADC module. Okay, then of course, then you have those other challenges of interfacing and writing the device drivers for that new ADC module and so on. Okay, so I mean, these are all, like I said, things that students have faced again and again. Okay, and sometimes it's unavoidable because maybe you were not really told some of the requirements up front. Okay, but in some cases, maybe if you had talked through some of this earlier, then maybe it might have been easier. Okay, maybe you might have chosen some other controller instead of the AD328. Okay, yeah, so again, this question is just more to make us think that you must look at all available options when you run into an issue. All right, and see what is a more practical solution to what you have. Okay, so let's move on to the last part of the slides, okay, which is on the LIDAR interface. It's more of just understanding the LIDAR interface in terms of communication mode. And all the information that I'm presenting here is from the data sheets. Okay, so in the studio folder, there are three PDF files, okay, which talk about the LIDAR interface, the communication modes, and so on, and then how to interface and how to get it to work. All right. Again, this is also important when you are going to work on a project, okay, and you want to buy some hardware, okay, some peripherals and so on. You want to make sure that whatever you're buying, whoever you're buying from, is able to provide you with some proper documentation on how to use it, okay, and preferably some sample or reference code. Okay, if you don't have all these kind of resources and you buy the hardware, then you are stuck. Okay, because you may not have enough information to know how to use the hardware that you have. Okay, so always, okay, make sure you have the resources, the data sheets, some sample code that is available before you decide that, okay, I want to buy this particular sensor or this hardware or something like that. All right. So for this LIDAR, okay, what we have is, as you have seen in the studio, we are making use of all the libraries already given to us. Okay, and here we are trying to understand the way in which it works. All right, so the LIDAR itself, again, is very much a slave. Right, it is waiting for the host to send it a request. Okay, and based on the request, it will reply. Okay, so there's always a request and there's always a response. Okay, whenever I send a request, I always start with a fixed byte, which is A5. Okay, followed by what is the command. Okay, what is the thing that I want the LIDAR to do for me. Okay, and subsequently, when the LIDAR responds back, it is always broken up into two parts. One is what we call the response descriptor, and the other is the data response. So the response descriptor basically tells us what kind of reply we're getting back, and it also tells us whether it is just going to be the data confined within that initial reply, or we are expecting more data packets to come after that. All right, so in terms of a response descriptor, the first 2 bytes are always A5 and 5A. Okay, so this allows the host, okay, in our case, the Rpi, to know that the LIDAR is actually responding to me. Okay, and after that, it also sets aside 30 bits to tell me what is the data response like. That means for this particular request that it received, is now replying back, correct? But when it replies back, how much data are you expecting to receive? So that is the data response like. Okay, and also it talks about the sending mode, whether it's single request with single response or single request with multiple response. Okay, so these are the 2 ways in which it can work. Whereas, okay, one is where the host sends a request, okay, and then the LIDAR does some operation, correct, and then it sends you a response, and that's it. Okay, once you receive the response, that's it. Then you do what you want, and then later, if you want, you send another request. Okay, so that is one way. The other way is multiple response, where I say start scan, for example. So when I say start scan, okay, that means I want the LIDAR to start scanning the environment and start giving me data. So when it replies with a response descriptor followed by multiple samples. Okay, that means these are all the data packets associated with the information that it from the scan. Okay, and then once it is done, that's it. Okay, and then I can subsequently send another request and so on. Okay, so these are the different types of communication modes that we have with the LIDAR. All right, there could also be sort of requests where you don't expect a response. Okay, so maybe you would have just said, okay, stop the motor. Okay, and then you will just take the information, perform the operation, and that's it. Okay, so this kind of communication protocol, okay, is again what we will also be having between the UNO and the Rpi. Okay, so in next week's studio, this is what we will also be doing. Only thing will be between the UNO and the Rpi, okay, where we will talk about how Rpi will send some command, how the UNO will interpret the command and carry out certain actions. Okay, so here we are looking at some specific message. All right, so the first message here is the get device info. So the get device info is basically to get some information about the LIDAR. All right, so as said before, the first byte is always A5, and then we need to send the command flag. So the command flag, okay, where do we get this information from? Again, we go back to the data sheet. So in the data sheet, if you go through, you will see a list of commands that we can send to the LIDAR. So if I want to get info, I need to send 0x50. And what do I expect as a reply? I expect it to give me the serial number or device info, example serial number. Okay, so you can see that in this, I just need to send the A5 and 0x50. Okay, and after that, what will happen? The device will respond to me. Okay, it will respond to me, and when it responds to me, it will always start off with A5 and 50 first. Sorry, A5 and 5A first. That is always the first 2 sync bytes. Okay, so the host knows that the LIDAR is responding to me, and then it will give me another 30 bits to represent how much data I'm going to send back. Then how much data I'm going to send back. So in this case, for device info, it will send me back a total of 20 bytes, and that includes information like model, firmware version, 1 byte, serial number, and so on. All right, so these are all again important information that you need. Okay, because sometimes when your device is not working or something goes wrong, you want to upgrade the firmware or things like that. Okay, you may need to know exactly what model you're using, what is the hardware version you're using, and so on. So you can maybe provide the correct firmware upgrade to your device. Okay. The other example here is getting the health information. Okay, so the health information tells us whether your LIDAR is actually functioning healthily, correct? Okay, so if it detects any error, okay, something to do with the sensor, the motor, or whatever, it will be able to send this information back to us, and then we can know that something is not quite right. Okay, so similarly, 5.2 is from the command table. Okay, so when we send A5 and 5.2, you will get back the response. Okay, and in this case, for the health information, you only have 3 bytes of information. Okay, and that 3 bytes will be the error code status and the 2 bytes for error code. Okay, so again, all this is not something that we decided. Okay, it is exactly from the data sheet, and we are just trying to make sense of how the LIDAR communication works. All right, and I mean, the code is all there for you to see. All right, and if you look at it, as long as you understand the sample code and you understand the data sheet, you can easily extend or use the same LIDAR in another microcontroller on your own. Okay, so even though we are using it in Rpi, okay, you can choose to extend it to another platform on your own, because once you understand the code, the example code and how the communication works, you can use that same interface in some other board as well. Okay, so before we end, I just want to show this link over here. So give me a minute now. So this one is we didn't quite discuss it, but I just want to show you a demo of this. Okay, so this ransack. Okay, so what is ransack? Ransack is basically the algorithm, okay, that the LiDAR actually uses, okay, to make sense of all the data that it retrieves. Okay, so I'm not going to go into the algorithm and the code here, but basically what it does is when your LiDAR scans, right, it receives a lot of points, all right, and how does it make sense of where is the line actually and what is noise? All right, so if I were to step through, okay, if I step through over here, what will the ransack algorithm do is you will start off with some random points to create a line, okay, and then in each iteration it will try to come up with a better line that makes sense with the data that it collects. All right, eventually, so you can see that right now the blue line has fewer points compared to the green line, so you still keep the green line. Okay, so until a point of time where any other line does not have a better fit compared to what you have, then you say that that is the line that you are going to decide on. Okay, yeah, so this demo, what I'm trying to show you is at the back end how your LiDAR actually decides how to form those lines. Okay, how do you actually form the line to say that that is a wall? Okay, and not some random point that just came off from the LiDAR. Okay, so it uses some algorithm. So this is one of the algorithms that it uses, okay, to estimate that fit line. Okay, again, this is just for your information only. All right, just to show you how the LiDAR actually is working. All right, now of course there are a lot of other algorithms out there, but this particular LiDAR does uses this particular algorithm called ransack. Okay, yeah, so yeah, so one more thing that I just want to talk about. I think the last time I talked to you about students who have a startup and the NUS enterprise wing and things like that. Okay, so today I want to just share with you one other group of students who I also have advised over the years. Okay, so these are all, so this is the platform that they came up with. Okay, so I'll just send you all the link. You all can have a look later. So this is actually from our CG students. CEG students, but they have came up with an entirely software-based startup called CodeU. All right, and basically it's similar to the idea of Scratch, okay, where they have a game-based environment to teach kids coding. Okay, so they came up with this entire sort of a 3D game environment. Okay, where you're supposed to it's a space-based 3D environment. And if you look at the team, okay, these are all our CEG students. Okay, he's just about to graduate. Okay, and this is the team. All right, so they're all our CEG students. Okay, so I was the advisor while they were building up this platform. All right, and like I said, so it sort of shows you that you don't have to be a CS student to create a CS sort of business, correct? So even though they're CG students, they very much came up with this idea, and so far it's going well. Okay, they're still receiving funding and they are building up this sort of business. Okay, and I hope it grows. Okay, but again, like I said, there are a lot of opportunities for you, okay, as students to explore and grow whatever idea you have. Okay, and if you start it off now while you are a student, you have a lot of resources to tap onto. Okay, a lot of funding, a lot of space, the makers lab and things like that. Okay, so always feel free to explore. Okay, and think of trying something out. Okay, while you are still studying. Okay, and if something picks up, okay, then you can extend it further and grow it even after you graduate. Okay, yeah, so that's all I have for you all today. If you have any questions, you can stay back and ask me. Okay, if not, I will see you all next week in the studio.
Prof, can I ask about question 1C?
Wait, 1C,
Yeah, the data frame question.
Okay, wait. Yeah, this one is it.
Yeah.
So what is the question?
Yeah, oh no, I meant the other one, the one with the start and stop bit one. Sorry. Yeah, this one.
Yeah.
So I just a bit confused about the sequence of the data part of the frame. Like in the notes, right? The bit number 0 is on the right and bit number 7 is on the left. Sorry, I mean in the notes, the bit number 0 is on the left and the bit number 7 is on the right. But then in this sequence, right, the bit number 7 is on the left and the bit number 0 is on the right. So I don't know.
Yeah,
In the actual
correct.
sequence
Yeah.
is
So basically, yeah, in this example, we are just drawing it as it is laid out in the bits, correct? But physically, how it will be, I would say, depends on the hardware. Okay. So in our case, what you say is correct. In the Arduino, you shift out the least significant bit first.
Oh, okay.
So it is actually in the other way around. Correct. So if you were to look at it from the Arduino Uno's bit frame, you will say that the least significant bit comes out first. Okay, but in this, we are just we're not factoring in that we're just looking at exactly how to interpret a data packet.
Okay, I get it. Okay. Thanks, bro.
Okay.
Yeah, Prof. May I also ask? Can we get to question 3?
Question 3, is it?
Yeah.
Yeah.
Yeah. So because here 960 is a number of data package, and 120 is the bytes. It's not really a number of data package. So how can we really use 128 to divide by 960?
Okay, so because even though it's 128 bytes, okay, but this 128 bytes, we actually must translate it into 128 data packets. And each data packet is actually 10 bits.
So here we're not using a convention that 1 byte is equal to 8 bits.
No. So instead of bytes, that's why I said you don't look at it as bytes, we look at it as 128 data packets. Because the bytes, the 128 bytes is what is stored in the buffer, correct? But
Yes.
when it goes out on the transmit line, okay, each byte already has a start bit and a stop bit.
Okay.
So it becomes 128 packets, and each packet is 10 bits.
Oh,
You understand? So the 128 bytes is the actual data, but when we transmit out, we're adding the start and stop to each byte.
I see.
Mm.
Okay, that makes sense. Okay, thank you.
Okay, wait. So there's a question in the chat right now. Question 2 and question 5C. Okay, question 2. Okay, so question 2 is just an example on the parity across bytes. Okay, so previously we know that this is what we did before. That means for each byte, we calculate a parity. Correct. So in this case, if I say it's an odd parity, that means the number of ones in that particular byte must be an odd number. Okay, so if I look at byte 1, I got 1, 2, 3, and 4 ones. Okay, which is an even number, so I say there's an error. All right, but because a parity can only detect error, it cannot correct the error because we do not know where the error is. Okay, we do not know where the error is. So since we do not know where the error is, we cannot correct it if I just do a normal parity check. Okay, so that is where this second level of check comes in, where I do parity check across bytes. So I do across bytes, that means what am I doing? That means I'm looking at each bit parity for across a certain number of bytes, in this case 3 bytes. So if I look at bit 7, the parity bit is a 0. Why? Because I have 1, 1, so it's odd number. For bit 6 is 1, 2, so I added a 1 as a parity, so become 3. Okay, and so on. So for each bit, okay, across the bytes, I generate a parity. So that is the parity across the bytes. Okay, so what we will observe is in bit 4 column, the number of ones is actually 2, which is an even number. Okay, which tells us that there is an error here. Okay, so tutorial question is wrong, is it? Okay, I need to go and check. Okay, but look at this example. So in this example, the bit 4, okay, column, the number of ones is 2. So it tells us that column in bit 4 also has an error. And we know that the row of byte 1 also has an error. So when I look at it both together, we can say that byte 1, bit 4 is the one that is wrong. Okay, and then I need to flip it. Okay, let me see. Okay, so 5C, what is the question? This is the same technique as in the studio, correct? Because we know that is basically a ratio, correct? Maximum voltage is 5 volts and that is 10 bit. Okay. So anything lesser than that is the ratio. So 3.6 over 5 times 1024. Okay. So again, this is based on the 5 volt mapping to 1024. But that is the highest voltage and this is the highest ADC reading. This one you just do a conversion, use your calculator. Using any decimal to binary converter, you can get the final answer here. Okay, so anything else? Okay, baud rate, like I said, the general definition is symbols per second. Okay, but again, like I said, because everybody has interpreted it a bit differently, if you go online and search, you will probably get a mix of answers. Okay, there will be a lot of websites that say it's bits per second. Some will say information per second or data rate. So you get a mix of answers if you go online and search. Okay, but generally baud is considered simple. So baud rate is symbols per second, and again, it's just that people have used it loosely over the years, so it has sort of morphed into bits per second. Yeah, so symbols per second is the more correct term. Okay, so if nothing else, thank you. I will see you all next week in the studio. Okay, thank you. Bye.